Hello, in this very lesson, we're going to continue working on, complex derivatives, and under complex derivatives, we're going to be looking at horizontal uniform circular motion. So today, we are looking at a car moving in a plane circular path. Now, in our previous lesson, under the horizontal uniform circular motion, we looked at a canonical pendulum. So today, we're looking at a car moving in a plane circular path. So let's try to have a pictorial, understanding of what we're talking about. So let's say this is, I'll try my best. I'm not very good at drawing, by heart. It's a circular path here. So let's say we have a car like this. So you have a car like this moving in this circular path, just like this. So you have a car. So you have a car like this. You have the wheels of the car, the mirrors, I mean, too. So let's say we have a car. This is not a perfect diagram, just manage and try to use this to explain this. So there's a car moving on this circular path. This is a circular path here. I have a car moving on the circular path. Now, don't forget, in our previous lesson on canonical pendulum, now it was said that it's the tension on the string. The tension in the string was actually in the previous lesson we said the tension brings about the centripetal force. So that's that for canonical. But for this, what brings about the centripetal, what helps this body to keep moving in this circular path is not, there's no string here, but what helps this body to keep moving in the circular path is the friction in the tires. So you have a friction here, you have another friction here. So if you don't have a basic understanding of friction, you may not really understand this. So I'll try my best to help you understand. So now this car moves, it keeps going like this in the circular path. Now, the friction on the tires, the friction, the major friction on the first tire and friction on the second tire, we're going to be using one tire. So the friction on this very tire is what helps this body to maintain movement in the circular path. It is not gravity, really. It's not gravity, it's the friction in this very tire. So now, how do we explain this? Let's look at the analysis, for this very stuff we have right here on the board. Don't forget, this is a plain, circular path. It's not banked. It's just plain. The body just keep moving, on this very plain path. So now, how do we explain this? Now, don't forget, everybody here has this. There's something we call weight. You have a weight. This very car here has a weight, a downward weight. So if there's a downward weight, it means there's going to be a normal reaction. Newton's third law of motion. For every action, there's an equal and opposite reaction. So as this body has a weight of Fw, which is equal to mass times gravity, there is a normal reaction, Fn. You understand that's going to what act against, that's going to counterbalance it. Let me use that word. So there's a weight from this body, this very car moving on this very circular path. There's a weight, the car has a weight, downward weight, while there's a normal reaction, probably, let's say from the seat of the from the driver's seat or whoever is driving this very car. So a normal reaction fighting back against this weight. So now what do we do next? Apart from that, we also have force of gravity, FF. So we have that very stated out. So we said this frictional force, I say force of gravity, I mean frictional force is what brings about, is what gives us, this gives us centripetal. Is equals to centripetal force. If not for the frictional force, this body would have moved out of the circular path. There will be a kind of skidding. It will move out. But due to the fact that we have frictional force, it helps us to achieve centripetal force. While this body moves, the friction keeps it moving towards the center of the circle. So now let's carry out our analysis. Now, sum of forces along the y-axis equals to mass times acceleration along y-axis. Acceleration along y-axis is 0 meter per second squared. Don't forget, there is no movement along y-axis. This is horizontal circular motion, uniform circular motion. So it's not vertical. So the body is not moving up and down. So acceleration along y-axis is 0 meter per second squared. So what are the forces? Sum of forces is a normal force, fighting against gravity, against weight, which is the mass of the car, times 0 meter per second squared. So the normal force minus weight mg equal to 0 Newton. We send this to the other side. So normal force is So normal force naturally is mass times gravity. That's what normal force is. Normal force is mass times gravity. Now, if the normal force is mass and gravity, now what's going to be? We are done with sum of forces along the y-axis. So the sum of forces along the x-axis will be mass times acceleration along the x-axis. Acceleration along the x-axis is what we call the centripetal acceleration. I like to use alpha, or you just use your a centripetal acceleration, or angular acceleration, which is equals to v squared over r. One of the major formulas, v squared over r. Okay, now what do we do next? So what are the forces along the x-axis? The forces along the x-axis, as you can see, is mainly the frictional force. There's no other force again, just the frictional force that we have. So it's going to be the frictional force equals to the mass times v squared over r. That's what we have. That's what we have here. And so now, when you talk about frictional force, quickly I'll just touch friction a bit, you know, because if you don't understand basic things on friction, you may not be able to understand this really. Just touch friction a bit. So according to the laws of friction, frictional force is directly proportional to the normal reaction. That's a law of friction. The frictional force is directly proportional to the normal reaction. So if that is it, so frictional force is equal to the coefficient of static friction or kinetic friction times normal reaction. So the frictional force is this. So frictional force is coefficient of friction normal reaction equals to mv squared over radius. Now this radius could be maximum speed. Don't forget that canonical pendulum, we talk about maximum speed that helps that variable to keep moving in that circular path. So here also we have the maximum speed. This is the maximum speed, that helps this car to keep moving, in this very circular path. So what do we have? We have this. Now we're going to bring this out. This here represents frictional force. So frictional force with coefficient of static friction or kinetic one times normal reaction equals to mv squared over r. So we're going to cross multiply. What do we have? We have this normal reaction times r equals to mv squared. So divide both sides by m. What do we have? We have v squared equals to this coefficient of static friction or kinetic friction times force of normal reaction times radius divided by m. So that v there, which is you can say v max, the square root of this whole thing. What we have here over mass. So that is that. That's that. So we have the v max is coefficient of static friction times normal reaction times radius over mass. Now, don't forget, normal reaction is mass times gravity. So if normal reaction is mass times gravity, it means, let's bring this here. If normal reaction is mass and gravity, it means the V max is equals to, what do we have? Okay, let's take it off to the other side there for better. Let's take it off to the other side. So what this simply means is this. So it means V max. So we have square root. So the coefficient of this static friction or kinetic times normal reaction. What's normal reaction? Normal reaction is mass times gravity, then times radius over the mass. So divide both sides by mass. So the V max or the speed is equals to coefficient of friction, static friction times gravity times radius. This is the basic formula for this. A car moving in a circular path, as simple as ABC. So this is the formula we're going to be using to solve this. Now don't forget, this car moving in a circular path, in a plain circular path. This car, moving in a plain circular path, there is no angle involved. There's no angle involved. So, and there's a major formula as simple as that. It is frictional force that brings about the centripetal force, which keeps this body moving in a circular path. So that is all for this. So I would love you to watch out for the next stuff, which is movement of bodies in a banked, not plane this time around, in a banked circular path. So we'll be drawing the curtain on this very lesson. If you found this lesson, helpful, follow me on Facebook and Revelation Up. Also, subscribe to this very channel at Edge Mosaic. Share this lesson also with others. See you in the next lesson. Bye for now.